Hi class, today we're going to be covering electron energy levels. This is section 4.6, and as you can see, we're going to be dealing with some colors in this topic. So electromagnetic radiation. We experience our whole lives, everything that makes us live the life we have is through electromagnetic radiation. We're going to break down what exactly that means. So electromagnetic radiation consists of energy particles that moves as waves of energy. We call these wavelengths, and the wavelengths are all different in energy levels. So the colors that you're seeing here are all different energy levels. High energy levels have a small wave, as what you could see here in the purple, and low energy levels are this red waves that kind of are not, you can think of these as tight curls, and this is more of a wave or a very loose wave or a loose curl, if you would. And the distance between these, how we measure these, is the distance between either one of the bottom parts is a trowel, it's moving, and from one to the next one, or the peak, top to top. And that's how we know. And you can see these are much closer together. So if you were to look at this as how do we know what's high energy, how do we know what's low energy? Think of these as people. If you count from one to another, you can see that in a certain amount of time, more of these waves are going to go through compared to these waves. So the purple, the blue are higher in energy than what you see is the yellow and the red. Here is an electromagnetic spectrum. And like I said, our whole lives revolve around electromagnetic radiation. Everything that we do involves this. We have radio, television, cell phones, power lines. And as you go, so if you take a look here, see the waves that are here, they're kind of very loose curls. These are lower in energy. So you see the wavelength here. So these are lower in energy. And as we start moving up, we have radio waves, microwave, infrared, ultraviolet. This is where we see things in color. This is visible light. So you see it's expanded out. And I told you that red is the lowest in energy. Purple is the highest. And then it goes to blue. And then on the other side of that is UV rays, X-rays. And the highest in energy is gamma. And you can see how these are very, very, very tightly curled wavelengths. So these would go by extremely quickly. So when I posted, this is a bigger picture, you can see these are tight. These are very tightly wound. These are not. So these are the difference in the energy levels for visible wavelengths. So atomic spectra. Where does all this going? This is all leading to a certain thing we're going to cover later in this presentation. Atomic spectra. When atoms are excited, they emit light of certain wavelengths, which correspond to different colors if they fall in the visible wavelength region. Each element produces a unique set of spectral lines. So if we take an element and we pass it through certain instruments, it'll give us a fingerprint of colors for that element. Since no two elements emit the same spectral lines, elements can be identified by their line spectra. So what this is telling us, if we do this for every element, is that there are energy changes occurring in that element. And we have found that what is causing these energy changes is the electron. So how are electrons arranged? We're going to break this down. So I want to cover a few things before I start going into this. Electron configuration, that's how the placement of the electrons are in each atom. They are placed in order of lowest energy to highest energy. They do not move freely around. They are only allowed in certain energy values. This means that there is, if you're walking up a pair of stairs, you can never walk in the region that is holding the stair up in a sense, these parts here. You can only walk in the flat horizontal parts, not the vertical parts. That is similar to allowed energy values and not allowed energy values. It's the same for electrons. They're only allowed in certain areas and not allowed in others. So I'm going to break this down, and I'm trying to compare it to something that you can relate to, because students have a hard time learning this in the beginning. So we're going to use Dodger Stadium. Dodger Stadium, you get a pair of tickets and you've never been to Dodger Stadium before. You need to find your seat. So you know that Dodger Stadium is where you're going, And then you have to go in more and more and more. So you start out very wide, and then gradually you will find your seat. How will you find your seat? Well, you will go into Dodger Stadium. You'll figure out what floor you're on. You'll figure out what section you're on, and then what row, and then you'll find your seat. So that's what we're going to do, and that's how you need to remember how to compare what we're going to talk about, because this is foreign. So it's a little hard to comprehend in the beginning, but just break it down that we're starting wide and we're pinpointing to where these electrons are located. Okay, so electron energy levels, The lines in an atomic spectrum are associated with the changes in energy levels in electrons. So in an atom, each electron has a specific energy, and that's known as its energy level. It's also called the principal quantum number, and it begins with a small n. So it's n equals 1, n equals 2, n equals 3, and so forth. N equals 1 is the lowest energy, n equals 7 is the highest. And it increases. So we start with 1 and we go out. So the ones that are closest and the lowest in energy are closest to the nucleus, and the principal quantum number levels that are further away, like 5, 6, and 7, those electrons are furthest from the nucleus. And this energy of electron is quantized. So now we're going to start fitting these electrons in only certain allowed energy values. So electrons and energy levels. Okay, so I'm going to explain how this works. The principal quantum number is 1. That's the lowest. And highest energy is 7. So this is similar to putting books on a bookshelf. Now you have to start at the bottom though. So we fill the books as N1, and then we fill more books in N2, which a certain amount of books are allowed on each level, on shelf. So we have 2 books on N1, we have more books on N2, and we keep filling this with a certain amount of books on each shelf until we run out of books. That is the same as how electrons are filled in an atom. We fill a certain amount on the first level, which is N1. We fill a certain amount in N2, and we follow the rules until we get to the atomic number that matches on the periodic table. So that atomic number is that address for that element, and we're going to start using it. So we need to know how these electrons fill up to that atomic number. So an electron can only have the energy of one of the energy levels in the atom. So, for instance, we can't go, when it means quantized, we can only go, these books, the electrons, if we look at it this way, we can only put electrons in these levels that are allowed here. We can never put electrons, or let's say the books, in the middle of the shelf where the wood is. We could not, no matter how much we try to shove that electron or book there, it can't go because it's a forbidden area. And that's what I mean. These are only allowed in certain areas. Now here's something the book doesn't tell you. When it means N, this is principal quantum numbers. That is equal to the period number of the periodic table. This says row because I couldn't find anything that said period on it that highlighted it like this. But period is also row because you go across. So N equals 1 involves hydrogen and helium. N equals 2 involves lithium and goes all the way across to neon. So N equals 1 is equivalent to the period number on the periodic table. So we are now getting from Dodger Stadium and we're moving in a little bit more. Oh, and one more thing. All the electrons that are filled in, for instance, N equals 1, those are all, the electrons are at the same energy level. They're all grouped together. Row 2, all those electrons with the same energy are grouped together on that one as well. Okay, so changes in electron energy level. So this is how we see colors. So when you see fireworks, this is actually what you're seeing. You're seeing electrons being excited and emitted and being moved out of their spot into somewhere else. And there's an energy that's created. And if that energy that's released is released in the visible wavelength region, we see color. So here's a nice, I found this nice little GIF here where you see an electron. Electrons are spinning. They're spinning like a top, and they're also moving very, very quickly at the same time. So they've got a lot of energy going on. And As an electron absorbs a certain amount of energy. So electrons just can't take any energy randomly. It's like a lock and key. They have to have a certain amount of energy, and each element has its own certain type of energy. It's just like each house has its own lock and key. If that key fits, then you can open the door. This is the same for electrons. If that certain energy matches the electron's allowed energy that it can take in, it will jump levels. So what happens here is the electron becomes excited when it takes in that energy. So it's like a kid with candy can't sit still. It's going to jump to another level. And when it does, it takes in that energy. So if you see this red arrow will come right now, well, not right there, and jump it up. This is very instantaneous. This doesn't last very long. It's very, very quick. And for some, it's quicker than others. And so some will stay a little bit longer, and I'll tell you why right now. So when it moves up, it's also now going to have to lose that energy. It's not going to stay on that that upper level. I talk fast, and I tend to mess myself up. It's not going to stay at that upper level because it's not stable. In chemistry, the number one thing about chemistry overall, and nobody ever says it, is stability. Chemistry, everything we work with wants to be in its most stable form, identity, substance, and it will always work towards that. And if you change it, it's going to try to work itself to whatever stability it needs. So it'll jump up. It's not stable, so it wants to come back down. When it does, it's going to release that extra energy. And if that energy falls within this right here with these, and what you're not noticing, I didn't bring it up. You see, this is 700 nanometers. This is 400 nanometers. So even colors have their own numerical values, and that numerical values only are for those colors. So it's also an address for a color. And if that energy that's being emitted, that's the word that we use in chemistry, is emitted. If that number matches an address for that color, you're going to see that color. So that's what is happening here. Now, these electrons that do this, these electrons are what is responsible for chemical and physical properties of elements. Electrons are the ones that do it all. So why do I have this here? Because what you're seeing here is electrons being excited and emitting color. And this isn't just one electron. These, we learn this as one electron or one atom, but there is billions and billions all in these substances, because remember, we can't see this with our naked eye. So what you're seeing here with these colors is electrons being excited and coming down. Now, had we been in person, this was the funnest lab. You would have done this in lab. You would have you would have had a wand, and you would have dipped these into solutions that you wouldn't know what the colors are. And you would heat these. And it's not dangerous because it's a very small amount, but it's fun because you get to see the colors and you got to determine what colors these compounds are giving off. And then you would have had an unknown and you would have compared it. And some of the things that I've noticed over the years of doing this, because remember I told you I've done the Saturday lab for 5 years. Some of the colors last longer than others. That means that the electrons stay excited way longer than others. Like potassium is it's almost instant. It goes off. You blink and you miss the color. Where copper stays forever, even when you use the wand on another color. If you don't clean it right, that copper will stick around and stick around and stick around. And if you notice, strontium and lithium, they're red, but one is a bright red and one is a dark red. So it's very interesting how you see these colors here. And there's way more. This is not all of them. But I wanted to put that up so you can understand. Okay, so now let's go back to identifying the addresses of our electrons. We are now on sublevels. And sublevels, so now let's think of Dodger Stadium. We are on what floor? What floor do we got to? The principal quantum level is Dodger Stadium. Now we need to get inside and we need to know where level our tickets are. This is where sublevels come in. We need to find out where our elements are the addresses. We're getting closer to the address. So we're probably, let's say, maybe the street or the city. It is an arrangement of electrons that determines the physical and chemical properties of an element. I already said about electrons. Each energy level consists of one or more sublevels. The number of sublevels in an energy level is equal to the principal quantum number of that energy level. So for instance, if I have an n equals 2, that means I have 2 sublevels. I have, beginning with the lowest energy, I have an S and I have a P. If I have N equals 1, I have an S. So that's how you look at this. The sublevels are identified as S, P, D, and F. The order of the levels start with the lowest energy and go to the highest energy. And this is a look at what it is. So N equals 1, we have one sublevel, it's an S. N equals 2, we have an S and a P. And I'm going to break these all down for you, why we see more of others. N equals 3. Sublevel is an S, a P, and a D. So in terms of knowing what to learn on here and students get stuck on is the definitions, the terminology. Understand what energy level means. Understand what sublevels mean and how many sublevels are in each. And I'm going to cover that and the type of sublevels. So we're going to cover all this. We're growing in and in and in to find our seat at Dodger Stadium. So S orbitals. S orbitals are the location of an electron described in terms of probability. So here's the thing. We can never pinpoint exactly the position and spot where an electron is. But what they've done through experimentation is discovered the most highly probability of where electrons exist based on all these experiments. And what they did is they got these clouds, and these really dense clouds are where the electron has its highest probability of being. And they did this over and over. And what they found when they were doing this is that S orbitals, the S sublevel, looks like a sphere. So we draw them as spheres because who wants to draw an electron density cloud like this? So we draw them like this, but what they actually look like this. And here we have an X and a Y and a Z plane. So the S orbitals are known as spheres. And what they are similar to is the 1s, lowest energy, it's small. The 2, N equals 2, so it would have a 2s orbital, is bigger than a 1s. And the 3s is larger. So these are, I don't know what you call those dolls, even though I have one. You take the doll, there's a smaller doll inside, and you take the other doll, there's a small. These can all fit within each other because the lowest energy have the smallest, and as you start going out, these get bigger for S orbitals. So they increase as the energy levels go up. P orbitals look like dumbbells, and there are 3 of them. So that's why when we looked here, you see that there's 3 P sublevels, P orbitals. So this starts with N equals 2. They are not on the first level because if you remember the sublevel equals the quantum number and N equals 1, there's only an S orbital for that. So these begin with N equals 2. Each orbital looks like a lobe or a dumbbell shape, and they're all positioned on the axis of X, Y, and Z. So that's why you see them all in different, one's on X, one's on Y, and one's on Z. But when you combine them, they all fit into this looking flower kind of thing. And this, again, if you saw, these would be little density clouds, and these were the highest probability of where electrons are found. Now, I want to point out, and I didn't do it on this one, each sublevel has 1 orbital. So if I was to ask how many electrons are on an N equals 1, remember N equals 1 has 1 sublevel, it has a 1s orbital. 2 electrons can fit into this, and that goes for all of these. No matter how big these are, each orbital, no matter what level, 1 orbital can only hold 2 electrons. So this is 2 electrons max, 2 electrons max, 2 electrons max. Same goes for these orbitals. 2 electrons max, 2 electrons max, and 2 electrons max. So P orbitals, 3 of them, the total max that can be held in these is 6 electrons for these. Now we're going higher in energy, and these are D orbitals. And now they are actually not on the plane. So you see we have only one that's on the plane here. It's an X and a Y. And there should have been a Z. This one's a Z, but it looks weird. It looks like a dumbbell and always remind me kind of like a pacifier that's got on both sides. And then these are all in the plane of the X, Y, and Z. This is how they've done all these experiments. These are the highest probabilities. I found a nice GIF that shows you what 2 electrons would be in here. So because we have 5, that's 2 electrons, 2 electrons, 2 electrons, 2 electrons, 2 electrons, can hold a max of 10 electrons and a d orbital. If all of this is confusing, that we're going to work on why we're doing this in next section. It's going to make sense in the next section, hopefully. But this is learning about where this is coming from in order to build up onto the next information you've got to learn for it. So this d level, these d orbitals have 5 orbitals, and each can hold 2 electrons. So d orbitals can hold 10, p orbitals can hold 6, and s orbitals can hold 2. And these have got 4 lobes, and then one that's just weird. All right, so we're not going to cover the F, because no, you don't have to worry about F. I mean, once we start doing electron configuration, I might ask you for something in F, but I'm not going to cover the orbitals here. That's a whole different type of chemistry. There are a maximum number of electrons that can fill each sublevel. So again, S equals 1 orbital, can hold 2 electrons. P sublevel has 3 orbitals, can hold 6 electrons. D has 5 orbitals and can hold 10 electrons. And F has 7 orbitals and can hold 14. Make sure you are understanding the terminology here, because this does get asked on exams and quizzes. And if you don't know what it's asking, it's really frustrating when you see the answer later and you knew what they were asking. You just couldn't decipher it in the question. And chemistry is wonderful with asking complicated questions like that. Okay, next one. Now, there's rules within an orbital itself. So we take one orbital and they can hold 2 electrons. But the problem is, I think I told you, electrons are constantly moving, but they're also spinning. So think of 2 magnets. You can't put 2 magnets together that have the same side. They become unstable and they repel. You can only put them in opposite directions. And that's the same here. You have to put one, we're going to draw electrons as arrows. That's what the next section will be. And you can only add into orbitals 2 electrons, and one has to be up and one has to be down. There's no set way which it has to go, but people tend to write the first arrow as up, the other one is down. But if you wanted to be creative and go against the rules, so be it, and put the first arrow down and the next one up. It's still okay. So the Pauli exclusion principle states that each orbital can hold a max of 2 electrons, which I've already stated. So no matter what sublevel you're on, if it has an orbital, can only hold 2 electrons. Electrons in the same orbital will repel each other, so you have to put them in opposite directions to cancel out their spins. So this is the Pauli exclusion principle. Now, let's go an overview of everything I've just covered. We have energy level. They tend to call this energy level or principal quantum number. Have to be aware of that. These match the period of the periodic table. So it goes up to 7. Number of sublevels. The number of sublevels matches the energy level. So n equals 1, it has 1 sublevel. N equals 2 has 2. N equals 3 has 3. N equals 4 has 4, and so forth. Now, how does that involve? So n equals 1 has 1s. N equals 2 has 2s and a 2p. This is 3s, 3p, and 3d. This one has 4s, 4p, and 4d, 4f to the highest. So 4 has the lowest energy all the way to the highest energy, because f sublevel is the highest. And then number of orbitals within it. 1s contains 1. 2, so 2s also contains 1. 2p has 3 orbitals in it. And let's jump down to d. D has 5, and f has 7. And so now you can tell how many electrons are held within it. So if we look at energy level 1, and I ask you how many electrons can energy level 1 hold, you would go across. It has 1 orbital. That means it can only hold 2 electrons. Energy level 2 has 2 sublevels. You have to account everything. So 2s, that means it can hold 2 electrons, because an orbital holds only 2 electrons. But you've got 2p. You have 3 orbitals here, and each can hold 2. So you have 6. So the total electrons that can be held in an energy level 2 is 8. But I might ask you, how many electrons can be held in the 2p sublevel? Now I'm only asking about 2p. 2p has 3 orbitals. It would be 6. So you need to understand the terminology that goes with this. It's not that students don't understand it. They don't know how to break down the question. and it's complicated. Like I said the first day, this is like learning how a new language in 5 months, and expectations are that you know it perfectly. Now, let's go to 3s. 3, energy level 3. How many electrons does that have? Well, we have a 3s, so that has 2. We have a 3p, also has 6, matching the 2p here. Has a 3d. 3d has 5 orbitals, which has 10. So there's a total of 18 electrons that can be held in an n equals 3. And I'm going to go through the same thing here. So 4 has 32. Why does it have 32 and not 18? Because it has a 4f level, which has 7 orbitals, and each can hold 2 electrons. So that's 14 electrons, and you add all these up, it equals 32. So here is our learning check. Indicate the type and number of orbitals in each of the following energy levels or sublevels. So this is covering everything. You have to figure out what terminology in this matches what part it's asking. So we have an n equals 1. And n equals 1 is an energy level. It is not a sublevel. So it is asking for an energy level, and it's asking for the type and number of orbitals in here. So remember, n equals 1 is equal to 1 sublevel. So it should have a 1s orbital, and it does. Okay. Now the second one isn't an energy level, it is a sublevel. So it's now asking a question about a 3p sublevel. So indicate the type and number of orbitals in this sublevel, where we already know what type it is because the type is 3p. But how many orbitals does a 3p have? And it has 3p orbitals. So this is an example of trying to understand the terminology and how to break down these questions. Break it down little bit by little bit till you understand exactly what it's asking. And that's it. Thank you.